So we've got to set up an integral to evaluate the volume of the solid generated when the below region is rotated about the x-axis. Now the first thing I like to do with these types of problems is to construct a sketch of what the graphs actually look like. So drawing our axes here, we're going to have y equals x squared, which looks a bit like this. And the y squared equals x, which looks a bit like this. Okay. So the region that we are concerned with is going to be right here, this region of intersect. So now that we have this information, what we should do is we should actually find the bounds of this region. So we have to solve these equations. We have to put them equal to each other. However, we can't quite do that because, as you can see here, this equation is implicitly defined in terms of y. So what we're going to do is it's easy enough to solve in terms of x. Y equals the square root of x, taking the square root of both sides. Now, if we were to properly solve this, we would actually have y equals plus or minus the square root of x. But we don't have to do this because if you look at the sketch right here, the part of the graph that we're concerned with is actually in the first quadrant. And anything that's not in the first quadrant we don't have to deal with. So all of this region in the fourth quadrant we don't care about. So essentially that's the graph of negative square root of x that we don't care about. So we can completely omit it from our equation here because all we care about is the graph of y equals the positive square root of x. So with this information in mind, we are going to set up an equation to solve for our bounds, and we're going to get x squared equals the square root of x. Now I could draw the algebra here for you, but it is easy enough to see that the solutions of this are 0 and 1, the two most trivial solutions. So now we have enough information to set up our integral. So we are left with pi times the integral from 0 to 1 of the square root of x squared minus x squared squared dx. There's our solution.